All right. Let's remind ourselves of what we did yesterday. And again, we will review tomorrow, and I'll give you some nice tips, but let's recall what we did yesterday. So what is the power series? Actually, the Maclaurin series representation for 1 over 1 minus x. What is it? 1 plus x squared plus etc. And what was the interval of convergence? -1, 1. Now what about this guy? 1 over 1 plus x squared. We could actually use, remember we used number 1 to come up with a power series for number 2. We basically replaced, right? We kind of wrote this as 1 over 1 minus negative x squared. And then we basically took this guy right here and put it in for x, yeah? Yeah? And in doing so, we got our power series. Okay? So, and that was what? 1 minus x squared plus x to the 4th minus etc. And what is the interval of convergence, right? X and x squared, like x versus negative x squared and absolute value less than 1. I mean, it's still going to be x and absolute value less than 1, correct? Okay, so that means the interval of convergence is still the same here, -1 to 1. Okay? What did we get for this guy? Do you remember? Remember what we did for this? Didn't we like multiply and divide? Or we divided numerator and denominator by 2. And we ended up with like 1/2, right, in the numerator. And then we thought of this as 1 over 1 plus x over 2, correct? And then we actually used number 2, the second thing, to get the power series representation for the third one, yeah? We basically took this guy right here and replaced x with, or hang on, so we replaced x squared with x over 2, essentially, okay, if you will, okay? If you want to think about it that way, all right? So when we did that, we ended up with this power series. It was like 1/2, it's going to be 1 minus x over 2 plus x squared over 2 squared, plus, minus, etc. Okay, and if you wanted to distribute that 1/2, you could also do that, yes? And what was the interval of convergence here? What was the interval of convergence? I equal to what? You remember? What was the interval of convergence? X over 2, an absolute value less than 1 means x and absolute value needs to be less than 2, which means x could be between where and where? -2 and 2. So the radius of convergence is now 2. And then, of course, this guy is just basically thought of as x cubed times 1 over x plus 2. So we could use the previous power series to get one for this, yeah? And I mean, I'm inclined to actually go ahead and distribute this 1/2 through here and then multiply through by x cubed. And so what is the power series going to be for this? Well, it's going to be 1/2 x cubed minus 1 over 2 squared x to the what? 4th plus 1 over 2 cubed x to the 5th minus etc., right? You kind of see the pattern. And what is the interval of convergence going to be for this? Same. -2 to 2. Okay? And then we left off last time with this one, 3 over 2x minus 1. And we wanted to make a power series. All of these power series are centered at 0. They're actually Maclaurin series, yeah? But on number 5, make the series centered at x equal to 2. Huh. Make the series centered at x equal to 2. Well, first of all, I think we can rewrite this a little bit. Maybe we could, multiply and divide by -1 and make this into -3 over, just to make this look a little bit more like something we're used to. -3 over 1 minus 2x. Just so it's starting to look kind of like, maybe like this guy up here, 1 over 1 minus x, sort of, yes? But then the thing is, I want this thing to be centered at x equal to 2. How am I gonna do that? What do you think? How am I gonna get something that's centered at x equal to 2? As opposed to 0. I could actually do an expansion right now and get something that's centered at 0. How am I going to get something that's centered at x equal to 2 without having to take tons of derivatives? That's what I'm saying, right? I could, in theory, kind of take derivatives and try to find a pattern, and we keep plugging in 2 to make a power series centered at 2 so that we have powers of x minus 2. What do we do? What do you think we should do? Yeah, Daniel. Mm-hmm. So could you plug in something like substitute x for x minus 2? Well, oh, right. So we want to, let's kind of erase this for a minute. And so what Daniel is saying is, it would be nice if instead of seeing like an x here, we saw like x minus 2 somehow, right? We could see x minus 2, we'd start to be making some progress. So let's see, if I want to write equals, I mean, if I could be so bold, let me write it this way. I'll write this as 2 over x minus 2 minus 1, but I know full well that these aren't equal yet. You know what I'm saying? I mean, I just like a maniac subtracted 2 from x, but that changed the denominator. What do I have to do to change it back? Add something, because think about it. If I were to distribute this 2, I would get the 2x like I had before, but I would also have a -4. You see what I'm saying? So what do I have to do to offset that? Since I've introduced a -4 down here, I have to offset that by doing what in the denominator? Add 4. Okay? So let's stare at that for a minute. So let's see here. This means I have 3 over, what is this? -4, or -1 plus 4 is what? What is that? 3. Right, this is 3 plus 2 times the quantity x minus 2. Okay, that's looking a little bit better. Instead of seeing an x, I at least see an x minus 2. Yeah? Now what am I going to do? Now what do we do? This is exactly the right approach. Okay, but now what do we do? That might mess things up. So I still want that x minus 2 there. I don't want to distribute that 2. But what did I do up here when I had this plus 2? Here I have a plus 3. Do you know what I'm saying? What did I do with that before? You divided top and bottom by 3. Does that make sense? If I do that, what do we get? If I divide top and bottom by 3, it's going to be 1 over 1 plus what? 2/3 times the quantity x minus 2. You see this? So now I mean, just so that we're clear, this looks like 1 over 1 plus x, basically, yes? Where x is that big thing in the red brackets. Yeah? See, it's like 1 over 1 plus x, where x is that big thing in the red brackets. And I know a power series for 1 over 1 plus x. What is a power series for 1 over 1 plus x? Yeah, 1 minus x plus x squared minus x cubed plus etc. And what's the interval of convergence for that again? -1 to 1, which by the way means -1 less than x less than 1. That's what I'm allowed to plug in, yes? That is going to be important down here, okay? Because I'm about to expand this thing into a power series, and playing the role of x is this thing right here. 2/3 x minus 2. That is playing the role of x. Do you see what I'm saying? I'm going to take all this junk and put it right in here, in for the x term. Okay? Does that make sense? Okay, so let's do that. Here, so let me, I need to erase the board here and kind of rewrite this thing, but so let me do that, okay? So actually I'm gonna go over, let's do this. I'm gonna actually go over and share this on a whiteboard, okay? So let's do this. Okay, so here's our whiteboard. Let's see. What was I doing? It was 3 over 2x minus 1. We rewrote this as 1 over 1 plus, what was it? 2/3 times the quantity x minus 2, because I wanted specifically to expand this thing with a center of 2, yeah? And then I went ahead and I'm going to use this power, I'm going to use the power series 1 over 1 plus x. I'll write it down here. 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus etc. with interval of convergence equal to -1 to 1, which means -1 is less than x is less than 1. Okay, and I'm going to expand this thing out. So it's going to be 1 minus, what's playing the role of x again? All that, yeah? So it's going to be 1 minus 2/3 times the quantity x minus 2. And what's the next term going to be? Plus what? 2/3 squared, what? X minus 2 squared. And what's the next thing going to be? Minus 2/3 cubed x minus 2 cubed plus etc. And before I needed -1 to be less than x to be less than 1, yeah? So what has to be true about this up here? -1 needs to be less than the thing that is playing the role of x, which is 2/3 x minus 2. That needs to be less than 1. All right, if I multiply through by 3/2 to get rid of the 2/3, that means that -3/2 is less than x minus 2 is less than 3/2. Do you follow? Yeah? And now finally, what am I going to do at the end here? I'm going to add 2. Okay, so what's x? What's the deal with x going to be? X will be trapped between where and where? 2 plus 3/2, which what is that? 3.5 basically, yes, or 7/2. 2 minus 3/2 is like 1/2, yeah? Okay. So by the way, I mean, this is like 0.5, and this of course is, what is that, 3.5? What is right in the middle of that interval? What's right in the middle of that interval, as it should be? 2, yeah? And what is the interval of, or what is the radius of convergence? So the center here is 2. What is the radius of convergence? What's that? 1.5, 3/2, right? Which, you know, is no doubt connected to the fact that, you know, x minus 2 was between -3/2 and 3/2. And the interval of convergence, excuse me, is 1/2 all the way up to 7/2. Okay? And, What do you think is, like, do you think I'm going to be able to plug in 1/2 and 7/2? No, for the same reason I can't plug in x equal to plus or minus 1 into this thing down here, okay? So that is the interval of convergence. Does that kind of make sense? We had to do a little bit of algebraic trickery there, but hopefully that makes sense. Any questions on that? Yeah, Maria. Oh, hey, you're here. Okay, great.
So for these, you're just trying to get it like in the form of one that you already know.
Yeah, and you remember, it's obvious that like the geometric series is like a big deal, right? I mean, we keep using different versions of the geometric series, for instance. But as I mentioned, the exponential, sine, cosine, logarithm of 1 plus x, those are things that tend to come up quite a bit as well. Okay, and those ones are easy to memorize also. So I would encourage you to do so. All right. Are we good? So that's a nice little example for us to work through. Let's go back to the section here and we'll continue. All right, so we figured out what that series was. All of these were related to the geometric series in one form or fashion, even the one that we wanted to center specifically at 2. So that's interesting. Okay, so I want to talk a little bit, and this is actually the close of chapter 9, which is exciting, right? I want to talk a little bit about operations with power series. So there's composition, or plugging in something besides x. We've already been doing that, haven't we? We've like been replacing x with other things at times, yes? Sometimes we replace it with x squared. Sometimes the last time we replaced it with 2/3 x minus 2. We replaced x with that. That's technically a composition that we're doing, yes? And sometimes you'll even plug a power series inside of a power series, believe it or not, okay? Composing one thing with another means you plug one function into the other function's variable. Yeah, that's what composition means, okay? Adding or subtracting 2 power series is a common thing. Differentiating or integrating a known power series, kind of like what we were doing yesterday in the last section. That's a common thing that we do, okay? Here's kind of, this is just a screen grab from the book. If I start with a couple of power series, f of x and g of x, okay, you know, one is just a and x to the n and going from 0 to infinity. The other one is this guy. If I replace x with kx, okay, so I'm replacing x with kx, then of course I just go into the power series and I get an extra factor of k to the n, yes? Because x becomes kx and k gets raised to the n power also. Of course, if I replace x with x to the capital N, then like if I replace x with x to the 5th, then all of the powers of x get multiplied by 5. Yes? And that's basically what this is saying right here. And of course, if I want to add and subtract, you know, these 2 power series, that just amounts to adding and subtracting things term by term. Does that make sense? So the coefficients of x get added or subtracted, the coefficients of x squared get added or subtracted, and they get slapped right on there. Does that make sense? I mean, there's nothing like super deep going on here. I just wanted to point out stuff that we have already seen kind of happening. We saw a situation like this. We replaced x with x squared, didn't we? Yeah? What that did is it kind of made all the powers multiples of 2. Yeah? Which was to be expected for sure, okay? There are other operations like division of power series, by the way. So for instance, look at this. Look, here's a little example. In fact, I'll just go in and I'll share this with you on the whiteboard, okay? This is sort of a weird thing, but watch this. 1 over 1 minus x. Okay, you guys know a power series for that, don't you? Yeah, but really, do you guys realize that this means 1 divided by what? 1 divided by 1 minus x. You can actually do a weird polynomial division with these things. You can say, all right, 1 minus x, that means I need to divide that into 1. okay? Now this is sort of weird. What you do here is you say, okay, how many times does, okay, you kind of do, you do polynomial division almost backwards. You say, okay, this one and this one here, okay, this, to get this one to go into this one, I need a 1. 1 times this is like 1 minus x, and I have to subtract this thing, and what am I left with? Now you're left with x because there were no x's up here. 0 minus negative x is just x. And then what you try to do, and this might sound like some kind of weird trickery, but you still stick with 1 as being the thing that you're trying to get to match up. What would I have to multiply 1 by to get x? X. And then you distribute this thing, right? I mean, every time we're just sort of distributing these guys, right? Okay. X times that is x minus x squared, and I subtract, and what happens? What am I left with? Positive x squared. And then what comes next? Yeah. So you again concentrate on this 1. It seems like you're sort of cheating, but I'm telling you, this is a valid way of doing this, actually. Okay. You add in x squared, which distributes over, and you get x squared minus x cubed. And what's going to be left next? X cubed. Yeah? Can you see what's going to happen? Is this ever going to finish? No. And up here, it looks like I'm getting plus x cubed, plus etc. So in other words, this thing appears like if I carry out the polynomial division in this weird way, I end up with 1 plus x squared plus etc. That's sort of strange, isn't it? So you can kind of see the power series produce itself through polynomial division, which is kind of weird, okay? But I can also do other weird things, okay? So let's go to the next slide here. So do you guys remember what the power series was for sine of x? What was the power series for sine of x? Right, yeah, so, okay, so, well, this was the odd terms that survived. So it was like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. What about cosine? I think that was the one that you were just saying, Drake, right? Cosine, that was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. So hey, what's tangent? Yeah, it's sine over cosine. Which, by the way, means sine of x divided by cosine of x. Do you know what I'm saying here? Yeah? So in other words, that means that I should take this power series here. This is sort of freaky, but you take that power series and you divide it by this other power series, yes? And the result of doing that division should give me a power series for tangent, yeah? Okay, so let's think about that for a minute. I'm going to take the cosine thing and divide it into the sine thing, yes? So let's kind of think that through for a minute. Let that cook our noodle for a second here. Let's see. So I'm going to divide that into, let's see, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, let's just go with it here. I mean, we're just literally flying by the seat of our pants here. So let's see, and then it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus etc. Okay. And we do that sort of backwards weird division here in this case. So what is the first thing I should do? So again, you concentrate on this guy right here. So what do I have to do to make the first term match? What would I have to multiply 1 by to get it to match the first term here? x. You see what I'm saying? And then that thing's going to distribute, okay? And look at what I'm left with. It's going to be x minus what? Uh-huh. Yeah. Okay, and then I subtract. And of course, what are you left with? Well, the x's go away. Know what I mean? Okay. But what are you left with in terms of x cubed? Well, it's okay. It's negative 1 over 3 factorial plus 1 over 2 factorial, yes? So it's 1/2 minus 1/6, yes? You guys see what I'm saying? Negative 1 over 3 factorial plus 1 over 2 factorial is what's going on with the coefficient of x cubed. Do you see what I mean here? Okay, so it's going to be 1/2, think about it, 1/2 minus what? And all of that is multiplied by x cubed. Exactly right. Now what about the next thing? Okay, plus, what's the next thing going to be? 1 over 5 factorial minus 1 over 4 factorial. Do you see what I'm saying? 1 over 5 factorial minus 1 over 4 factorial. So that's like 1 over 120 minus what? 1 over 24. Okay, and that's x to the 5th plus etc. Okay, let's not get ahead of ourselves here. Okay, so let me ask you, what is a half minus a sixth? I mean, I think we can all do that, right? What's a half minus a sixth? That's a third. See what I mean? So that's a third. And what about 1 over 120 minus 1 over 24? Okay, because it's going to be minus 1 minus 5. So isn't that negative 4 over 120 or something? Does that make sense? So you would multiply and divide the second thing by 5. You get negative 4 over 120, which, by the way, what is that? Negative 1 over 30. Thank you. Okay. All right. So what am I going to do next to try to make things work out? Because this guy right here is really just a third. And because this guy right here, what is that? That's like negative 1/30. Is that right? Oops. I'm getting trapped. I'm getting trapped on the bottom here. Okay. So what would the next thing be if I were to do this? Yeah, plus 1/3 x cubed. Okay. And this thing would kind of distribute over here. And hey, let's just let's just stop there for now. Does that make sense? But do you see how this would go? In theory, you could come up with a power series for the tangent function by using the power series for sine and cosine. Yeah? Okay, so I just wanted you to kind of be aware of that. Yeah. Well, because I'm comparing this guy. Okay, let me kind of mark it in blue. I'm comparing this guy and it's minus this guy. Yeah? So it's minus negative 1/2, which is plus 1/2, minus 1 over 3 factorial, which is a 6th. Does that make sense? Okay. All right, any other questions on that? Now let me ask you, what would you expect? What kind of a function is tangent? Is it odd or even? Odd. What did you notice is surviving immediately here? I mean, again, this is a power series centered at 0, but what powers of x seem to be surviving? Odd powers. Yeah, so that's kind of an interesting little factoid. Okay. But as you can see, you have more power than you realize, even with just these like basic power series functions in Pocket. Okay. All right, but we'll stop right there on that one. Okay, you could think about the next term if you wanted to. That would be sort of interesting, but I'll let you go do that on your own. Okay. Okay. So last couple of things here, just to kind of make sure we're on top of things. Adding two power series. So x over x squared minus 1. Okay, you could actually, look, what I mean by adding two power series, one way that you could do a power series for this thing is you could write this as x over what? X minus 1, x plus 1, and then you could do a partial fraction decomposition, and you could invoke the known power series for like 1 over 1 minus x and 1 over 1 plus x. And you could add those two things together with whatever constants end up being involved. But that's not the only way to do this one. We could actually easily come up with a power series for this because it's like negative x times 1 over 1 minus x squared. Do you see what I'm saying? Isn't that the same thing? Yeah? And then what could I do to kind of come up with a power series for this? Negative x, I have 1 over 1 minus x squared. What could I use to come up with a power series centered at 0 for 1 over 1 minus x squared? Geometric, yeah? So it would be 1 plus, used to be x, but now it's what? X squared plus, used to be x squared, but now it's x to the 4th. So it'd be 1 plus x squared plus x to the 4th plus etc. What would the interval of convergence be for this? Negative 1 to 1, yeah. So that would be one way to get a power series for that. Okay, now look at this. 1 over 1 minus x, as we know, is just 1 plus x squared plus etc. Yeah? On the interval from minus 1 to 1. And by the way, this guy is equal to 1 minus x to the negative 1, if you think about it for a few seconds, yes? So what happens if I take the derivative of this? Okay, so if I take the derivative of this thing, the left-hand side becomes negative 1 minus x to the negative 2. Yes? Okay, negative 1 minus x to the negative 2. And what does the right-hand side become if I take the derivative? 1 plus, what's the derivative of x squared? What would the derivative of x cubed be? Right? So look, if I differentiating this power series, I happen to find a power series for this guy because after all, negative 1 over 1 minus x quantity squared is exactly what I have over there. So in other words, this thing has power series equal to 1 plus 2x plus 3x squared. And what do we know is true? Plus 4x cubed, etc. What do we know is true about the interval of convergence for the derivative of a function? Which this is basically the same, yeah? Except at the endpoints potentially. But did I even have the endpoints for this thing to begin with? No. And when I take the derivative, the best I can hope for is losing endpoints. I never gain endpoints, right? Okay? So the interval of convergence here is going to be exactly the same as it was before. Okay? All right, I already kind of, I showed you the tantalizing possibilities with the tangent function by dividing two power series, yes? But what about arc-trig functions? Like, what about things like arctangent? Okay? What about arctangent? Well, it turns out that the nice thing about arctangent, if f of x is equal to arctangent, think about it, what's f prime of x? What's the derivative of arctangent of x? 1 over 1 plus x squared, right? But that has a power series expansion, doesn't it? Didn't we already come up with that? What was the power series for that? 1 minus x squared plus x to the fourth minus etc. Yes? That's the derivative of arctangent. So how do you think I could get a power series for arctangent? What do you think I could do? Integral. Integrate. Integrate. So if I integrate this thing, so that's supposed to be an integrate symbol, but I got a little excited there. Integral, let's see. What is that going to be? So the antiderivative of 1 over 1 plus x squared is equal to arctangent of x, right? All I did was just integrate this thing. Yeah, I integrated that thing. And what am I going to end up with? Well, what's the antiderivative of course I have to put a c here, which is a little bit annoying. You know what I'm saying, right? What is the antiderivative of 1? What is the antiderivative of 1? Yeah, right? So right now I'm integrating this thing term by term. The antiderivative of 1 is x. What is the antiderivative of negative x squared? Minus 1/3 x cubed. Very good. Okay, what's the next one going to be? Plus 1/5 x to the fifth. This should kind of remind you of the logarithm power series, except here I only have odd terms. Okay? Minus, etc. And after the nightmare that the tangent function was, it's kind of interesting that the arctangent power series gave way so easily. Okay? Now, what is the interval of convergence for this thing? Oh, by the way, what about C? What's the arctangent of 0? Arctangent of 0 means the angle whose tangent is 0. What angle is such that tangent of it is equal to 0? 0. So actually, this constant term right here ends up being 0. I can kind of get rid of this thing, right? That thing's 0. So I get that arctangent of x, think about it, arctangent of x is equal to x minus 1/3 x cubed plus 1/5 x to the fifth, and you see the pattern, minus etc. What is the interval of convergence? Before it was minus 1 to 1, right? Remember when we integrate, we might actually gain endpoints. Do we gain an endpoint? Think about it. What if I plug in 1? What kind of a series do I get? If I plug in x equal to 1, what kind of a power series do I get? An alternating 1 minus 1/3 plus 1/5 minus 1/7. It's an alternating series, and the terms without the minus signs are decreasing to 0. Therefore, the alternating series says I have convergence at 1. What about at minus 1? Think about what happens when I plug in minus 1. Same thing. If you get an alternating series, except the signs flip around, yeah? It's the same thing. So this thing actually converges at both endpoints. That's weird. Okay, it actually converges at both endpoints, which is interesting. Okay? Now, yes? I plugged them in here. In here. So if I'm plugging in 1 and -1 into this, I'm seeing like if I plug 1 in, I get 1 minus 1/3 plus 1/5 minus 1/7. Is that a converging series or not? Yes. What if I plug in -1? It's just the opposite, right? Because the powers are odd, it flips all the signs around. So it's still converging. So I end up getting an interval of convergence of -1 to 1. Yeah. Now, the last thing I have on here is I'm making a note to myself, do the pi example. What do I mean by that? Well, it turns out that the arctangent function has some nice features that we can take advantage of. Okay, so let me go over into the whiteboard here. Okay, so what did I get? I got that arctan of x was equal to x minus a third, x cubed plus a fifth, x to the fifth minus, etc. Right? And what was the interval of convergence? -1 to 1, and now I get to include the endpoints, which is kind of nice. So in other words, this is kind of interesting. Arctangent of 1 apparently is equal to this power series evaluated at 1. So what is that? 1 minus a third plus a fifth. What would the next term be? Minus a seventh plus a ninth minus etc. Right? But what is arctangent of 1? Think about it. Arctangent of 1 means the angle whose tangent is 1. The angle whose tangent is 1. At what angle is the tangent function equal to 1? Pi over 4, because sine and cosine are equal there. Do you know what I'm saying? So the arctangent of 1 is literally pi over 4. So look, what do we have here? We have a formula that says pi over 4, look at this. Pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth minus etc. So guess what? I can actually use this series to approximate pi. Isn't that kind of neat? Yeah? So pi is equal to, and by the way, Sir Isaac Newton was the first person to sort of realize that you could do this, and he just blew all other previous approximations for pi out of the water. Okay? Pi is equal to 4 times this series. 1 minus a third plus a fifth minus a seventh plus a ninth minus etc. So here's the thing. If I wanted to get a really good approximation for pi, what would I have to do? Just take as many terms as I want of this series and then multiply the result by 4. Does that make sense? Okay. So I don't know. I thought I would kind of end by us going in here and actually doing that. Okay, if you would just, you'd be so kind as to indulge me for a moment here. Okay. Okay, we are literally done with chapter 9 at this moment, which I'm sure is exciting for everybody. But let's actually go and compute this thing. Okay, so let's go to Wolfram Alpha, for instance. I'm going to go 4 times, what is it? It was 1 minus a third plus what? Oh man, look, somebody's been doing this. See this? I'm sure it's somebody in here. Okay. So let's do a few more. So what would the next one be? Plus what? 13th minus 1 over a 15th plus 1 over a 17th minus 1 over a 19th. I don't know. You could just sit here and do it all day long, right? So look at that. Do you see that giant fraction that we're getting? By the way, we're getting a better and better rational number approximation of pi, but pi actually is irrational. Okay? I'm going to do a couple more, okay, just because I'm obsessed here. 1 over 23 plus 1 over 25, etc. How close is this actually numerically to the true value of pi? Let's see. Not very good yet. It's like 3.21. Did I mess up? So a third, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. Right? But it's getting better, okay? You just have to take more terms to actually get this thing to be better and better and better, which is sort of interesting, yeah? Okay? All right. I think that's all I have for now. Tomorrow we'll talk a little bit about the test. Is that the one in Is that the proof that they use?